I'm going to talk about a project we have ongoing to do regional dynamical downscaling for the western United States. Okay, this project is a joint project with Oregon State University and the University of Oxford. We also have support from the UK Met Office and a postdoc who's recently moved to the Union of Concerned Scientists. It's a significant team. I won't go through the names. Those are the ones who are currently involved in it. I apologize to the past members who aren't listed. And we've had a variety of funders, from Microsoft to the USGS to the REACH program and others. I want to start with providing the motivation for this project, and it's really the uncertainty that's inherent in any climate change projection. And there are three major sources of this uncertainty. The first one is the internal system variability, and by the system I'm referring to the atmospheric and ocean circulation, and could also be the land surface. The ocean and atmospheric circulation patterns change, as we know. They're variable, and they're going to continue changing, despite human action or the lack of. So that's not going away. The other source of uncertainty is our incomplete understanding of how our system behaves. We understand many of the parts. We don't always know how when they act together, what the outcomes will be. Often when we do know the physics, knowing exactly the best way to implement that knowledge in a climate model isn't always clear. The third source of uncertainty is the future of human activity. We can speculate as to how many greenhouse gases we will emit over the next 50 to 100 years, but we don't really know. We have to cope with these uncertainties. As a scientist, I'm optimistic that our understanding of the system behavior will improve, and that source will get smaller. The other two aren't going to get smaller. In fact, at the rate of population growth and technological advances, I don't see the future of human activity. I don't see that uncertainty getting smaller. We could have a philosophical discussion. It's probably going to get bigger. So what do? Our approach is to include these sources of uncertainty as best we can in our climate modeling approach. Each one of these sources, we have a different tactic or method of incorporating it. For internal system variability, what we do when we run a climate model is we alter the initial conditions of the model, or what is the state of the atmosphere at day zero. And I like to think of the butterfly effect. You have a butterfly who flaps its wings in Mexico and sets off a typhoon in Indonesia. And if that butterfly, if you move that butterfly to the other side of Mexico, or he flaps his wings in another direction, that typhoon may not happen, or it might happen 2 weeks later, or it might hit Borneo. So what we do is essentially between runs, we what I call redistribute the butterflies and rerun the model, and we do this as many times as we can. To deal with our incomplete understanding of system behavior, what's frequently done is to use a suite of climate models. Our approach is a little bit different. We only have one climate model, so what we do is we vary the model parameters within that model, with the understanding that we don't really know what the exact parameterization should be. So it's essentially tuning the knobs and rerunning the model with different tunings. And then dealing with the future human activity, we might consider different greenhouse gas or land use scenarios out into the future. So we now have, we're changing things in at least 3 dimensions here, so you can imagine when you consider all the different possible combinations, you can end up needing a lot of simulations. And that's where the super ensemble name comes from. Typically and historically, we've had global climate models, which are coarse resolution. Some of these are run really maybe one simulation up to several tens. Those are the blue dots. This is a plot of spatial resolution versus the number of simulations that might be available. When we go to regional models at fine resolution, we tend to have many fewer simulations per model. But you'll notice the interesting space is the empty space, and that's more important for impacts analysis. We want fine resolution models, and we want a lot of runs. So that's where we want to go. And that's where our project aims to be. It's been called climateprediction.net, or more recently weatherathome.net. So briefly, our experimental design, we're running simulations for the historic period, roughly the last 50 years. We're varying initial conditions, and we're varying our model parameters. So we're just redistributing the butterflies, and we're tuning the knobs. And we're running it as many times as we can have the capacity to. For the historical runs, we're using observed sea surface temperatures. So and we're using an atmospheric circulation model, not an ocean circulation model. And then we've just started running simulations for a future period, 2030 to 2049. And we're also varying initial conditions. To deal with the future, because we prescribe the sea surface temperatures, we need to make some assumptions about how the sea surface temperatures will change with given anthropogenic greenhouse gases. So we're covering two of those sources of uncertainty. Currently, we're leaving out the third because we're only using one future scenario, the representative concentration pathway 4.5. Part of the rationale is that out until the middle of the 20th century, the scenarios don't vary too much between them. So that the results, if you go out to 2100, they start to diverge. But if you're out into the 30 or 40 years into the future, the differences aren't so great. But if we have time, we'd like to implement other RCPs. So we have a regional model of the Western United States. The resolution is 25 kilometers. It's embedded in a global climate model, which has a resolution of about 1.5 degrees. The global climate model feeds the boundaries of the regional climate model. We are generating way more runs than we could possibly do in-house. So we rely on a network of volunteers across the planet. This is a map showing their locations. This map is a couple of years old, so the dots we've added some dots and lost some dots. We often have about 40,000 active volunteers at any one time. So what we do is we send a packet from Oxford that contains the model and the data required to run the model. We send it to a volunteer, Aunt Maggie in Tampa. It grinds away on her PC for about a week when she's not using it. And then it's downloaded to our OSU servers where we begin analyzing the data. And when Aunt Maggie isn't using her computer, she can opt to have this screensaver, which gives her shows the progress of a particular simulation. So we have over 1,000 runs per year for the historical period. Ignore the colors, just look at the total. So that's at least 50,000 years of runs to analyze and multiple terabytes of data. So what have we seen so far? We can use the model to look for robust trends in the historical time series. And that's because we have so many simulations that we can start averaging out the internal variability component I was mentioning. So here's an example of the increase in temperature over the Pacific Northwest from 1960 to 2010. There is an upward trend. There's about a degree of warming during that period. But that time series has at least three components in it that make it look like what it does. One is sea surface temperatures. The other is the internal variability of the atmospheric circulation. And the third is the increase in greenhouse gas forcing in the background. So what the super ensemble allows us to do, and that's in the upper figure, is to, in a large regard, average out the internal variability and get the signal behind it. So what you see is in the black dots are the average of multiple simulations. And that time series is a function of sea surface temperatures and anthropogenic forcing alone. And as you can see, the trend is not too far off from the observed warming trend. Another interesting robust trend we see is the loss of the April 1 snowpack over that 50 years. The simulations are on the left, And again, I've smoothed out the internal variability that is sort of the noise that's hiding our signal. As you can see over the western United States, it's pretty much all, the trend is all negative. And on the right, I have a figure from a paper by Phil Mote showing that the observations and the models are pretty consistent with each other in terms of showing region-wide snowpack loss. Now that's looking at long-term trends. Another thing the super ensemble allows us to do is look at the distribution of a particular variable. So we can start looking at what happens at the extremes. In this case, I pulled out the summer maximum temperature from every year in the historical period, and I plotted it as a return period. So what you're seeing is, what you're looking at is essentially the likelihood of a summertime temperature being surpassed in the 1960s, which is the green line, and the 2000s, which is the red line. And we can pick out the 1 in 100 year event, what it would have been in the 1960s, about 42 degrees in this particular example. And if we want to look at the change, we just shift the arrow over to the red line, and we can see that the return period for that same magnitude event is now about 1 in 30 years, or a decrease of about a factor of 3. Now that's interesting, in the past, but a lot of people here really want to know what's going to happen in the future. So we're only really starting to look at the future runs. But I want to point out a relationship that's popped out that I found quite cool, or hot. So you're looking at the temperature change in Oregon and Washington from a baseline period out to the 2029, 2048 period. It's the degree of warming on the y-axis plotted against elevation. Pretty strong relationship between warming and elevation. And at the higher elevations, you're getting an additional warming of 1.5 degrees. And I don't see statistical downscaling approaches getting you this level of regional information. They're not embedded in there, so I think a challenge for us is to use this information we get from dynamical downscaling models and use that to improve statistical downscaling methods. I think that would improve our, maybe not our faith or our belief, or maybe even the practicality of the statistical downscaling data that we're using currently to run impact assessments. We don't use too much dynamical downscaling data these days. Now we're looking into why this relationship exists, and it's we haven't looked at the energy balance yet, but we think snow seems to play a role. So here I plotted the same temperature change against the decrease in the snowpack, and you can see a 25 centimeter loss in snow water equivalent means also an additional nearly 1.5 degrees of warming. So I leave it up to the ecologists to consider the ramifications of that. So we've used the model so far to look at robust trends over the last 50 years. We're just now looking at what the projections are from the future. What's really stood out to me so far is the strong temperature elevation snowpack association. I think we need to use this information to improve our statistical downscaling approaches. And that's it.